Okay, so now we're on to our third reaction type, double replacement. So single replacement was a lone element replacing an ion in a compound. Double replacement is where we actually have two different compounds where the ions are basically like trading partners. So, for example, in the illustration up here, I have AX plus BY. Well, A and B would both be like the cations, so you could consider them to be like changing partners or trading, like, you know, like they're dancing on the dance floor and they trade dance partners. So A is now going to be paired up with Y and B is going to be paired up with X, so you get two new compounds. And then under note it says these reactions will not actually take place unless the product includes an insoluble ionic compound or a molecular compound. So let's take a look at predicting one of these, and we'll see what that means. So first of all, your reactants are always going to be aqueous here. So let's say we take some sodium chloride, and that's going to be aqueous. And the physical states do matter for double replacement, so I'm going to write them each time. And I'm going to get, let's go say we react that with some lead 2 nitrate. That's also aqueous. Okay, so if they just if the positive ions trade partners, then that means that sodium and lead are trading partners. So sodium is now going to be paired with nitrate, and they're going to be in a 1-to-1 ratio because sodium is +1 and nitrate's -1. I'm going to hold off on the physical states here for just a second and explain that in just a second. So now lead then would be paired with chloride, and it is lead 2. So it was lead 2 originally, which is why I had 2 nitrates, and so it's still lead 2 on this side, on the product side, which means I'm going to have 2 chlorides. Okay. Now before I go to the trouble of balancing, let's take care of this little note. Let's make sure that this reaction actually happens, otherwise we're just kind of wasting our time balancing it. Notice I haven't written any physical states yet for my products. That's because we're going to use the other tool that's in the back of your periodic table, or on the back of your notes sheet that we're using right now, called the solubility rules. Okay, so the solubility rules basically just tell us what's soluble and what's not. And for a double replacement reaction, that's going to be important because one of our two products, either sodium nitrate or lead 2 chloride, has to be insoluble in order for it to be a reaction. Okay. So if they're both soluble, if they're both aqueous in the end, then this is a no reaction. And a lot of times it's asked, well, what if they're both solids? What if they're both insoluble? And that just doesn't happen. So it's either going to be one of them is soluble and the other one is not, or they're both soluble, in which case it's a no reaction. So let's learn how to use the rules here. Let's start with sodium nitrate. So that's my first product. I'm just going to rewrite it right here just so we have it to look at. So sodium nitrate falls under two different rules, actually. I'm going to focus on the negative ion rule because most of these rules have to do with the negative ion. So if I find the rule for nitrates, what that's telling me is that any compound that contains nitrate is soluble. And in fact, there are no exceptions to that rule. Some of these rules have exceptions. That rule does not. So that means anytime I see sodium nitrate, it's going to be aqueous because it's soluble. It can be dissolved. Okay, so that's one of my products. So one of my products is sodium nitrate, and so I just decided that is aqueous. If the other one is also aqueous, then this is going to be a no reaction. So let's see. So lead 2 chloride. So again, I'm going to write this just to kind of keep track of stuff here. So let's look at the negative ion chloride, because again, the rules generally are for the negative ion. So chloride has the same rule as fluoride, bromide, and iodide, the other halides or halogens, and that is that they are generally soluble. However, there are 3 exceptions. So most chlorides are going to be aqueous, but if the positive ion is silver 1, lead 2, or mercury 1, they're going to be exceptions. So what that means in this case, we do have lead 2+, and so that's an exception. In other words, it's an exception to it being soluble. which means it's not soluble, which means it's going to form a solid precipitate. So this product, PbCl2, I'm going to write solid next to it, and that's important because if both of these had been aqueous, we would have simply drawn a line through our products or erased our products and written no reaction. So this is a reaction, which means I do need to go ahead and balance it. So nitrate, it looks like I have 2 on the left, so I'm going to put a 2 in front of sodium nitrate on the right, which means I need to balance my sodiums on the left with a 2, which also turns out that it balances my chlorides as well because I have 2 on the right. So kind of get rid of some of the rest of this stuff, and there's my balanced equation. Okay. Another thing that could happen is you could get a molecule. So let me give you an example of that. HNO3, again aqueous, plus let's say calcium hydroxide. Aqueous. Oops. Okay, so again, the cations are going to trade places. In this case, H would act as a cation even though it's a nonmetal. And calcium is going to act as the other cation, and they're going to trade partners. So I'm going to get, as one of my products, calcium nitrate. Okay, and I'm going to go straight to my rules because now I know how to use them. And my rules, previously, I learned that nitrates are always soluble with no exceptions. So I'm going to say aqueous for calcium nitrate. Okay, and then what would my other product be? Well, I've got hydrogen over here paired up with hydroxide. So hydrogen hydroxide is just water, right? I could go down and look at my rules for hydroxides and decide whether it's soluble or not, but it doesn't really make sense to ask the question, is water soluble, right? Water is, like, you know, water is what is the solvent when we talk about solutions. So asking whether it's soluble or not doesn't make much sense. Of course, at room temperature, it's not aqueous or solid, it's a liquid, right? So you might say, well, this must be a no reaction because I didn't get a solid precipitate forming. But if you'll notice, the reaction will not take place unless the product includes an insoluble ionic compound or a molecular compound, which water definitely is. It's covalent. Okay? So the last step here is just to balance. I've kind of made my equation a little bit messy, but if I balance, it looks like my nitrates need to be balanced. And then my hydrogens on both sides, I've got 2 plus 2 is 4 on the left, so it looks like I need a 2 in front of water on the right, and that gives me 2 oxygens, and I have 2 oxygens on the left, so it looks like I'm balanced.